Okay, so today we're going to lecture on inverse functions. This week we have online office hours today. So that goes 8 to 9 p.m. Tomorrow I have on-campus office hours, so I want to make sure everybody is aware that these are on campus. Tomorrow they'll go from 4 to 6 p.m. Wednesday I will be on campus. And those hours, unlike, it says something on your calendar, but I'm going to do this from 11 to 1, 11 a.m. to 1 p.m. on Wednesday. Also notice that on Wednesday, no live lecture on Wednesday. So this will be the only lecture of the week, is today. On Thursday, the testing window opens. So that's obviously a big deal. And that runs October 26th through October 31st. Also on Sunday, this coming Sunday, I'll have online office hours again. From 7:30 to 9 p.m. You have web assigned homework on sections 5.5 and 5.6. That's due October the 29th. I delayed that from, I think it was originally October the 27th, so I gave, or something like that. So I gave you a couple extra days for those two web assigned homeworks to be turned in. So that's kind of a week in review here. And so this is a test week, so you should be getting ready for that test. So, Amber, do you have any questions that you wanted to ask about before we got started? Okay, so this is section 5.5, number 5 on WebAssign. Okay, so the way I would ask this question is I would give you this function, and I would say, given x minus 3 is a factor, find all other factors. Find all other zeros. Or actually, not even find all other zeros, just find all the zeros, and just in general. Okay, so what we know is that if x minus 3 is a factor, that tells you also that 3 is a 0. Remember that those two things go together. The factors and zeros always go together. So if you have a linear factor for a polynomial, then you automatically get a 0. And if you have a 0, you get a linear factor. Those always go together. So notice I have a double-ended arrow between those two. That means that you have one of those, you've got both of them. So if you've got a 0, that means that if I divide synthetically by 3, like this, I better get 0 as the remainder when I divide right here. Also remember that there is no x term, and because there is no x term, you have to make sure you put in the placeholder. An x term is missing, so I have 0x there, and so notice I put a 0 down here in the coefficients as well. Easy to overlook that if you're not careful. So I bring down the -9, I go through the synthetic division, I get -27, I add, I get 1, 3 times 1 is 3, I add, I get 3, and then 3 times 3 is 9, add on, I get 0. So what this means is that x minus 3 is a factor, we already knew that, but we also get the other factor, and the other factor would be -9x squared plus x plus 3. Now you hope that factors, and if it factors, then you can get the other two zeros easily, that quadratic that I've got. But this quadratic is not factorable. You try to factor it. Try to factor the quadratic, but it's not factorable. And because it's not factorable, then the only choice to find the other zeros for the polynomial is to use the quadratic formula. So you have negative 9x squared plus x plus 3 equals 0, and you have to use the quadratic formula to solve this equation. Now, I usually do not like that first term being negative when I use the quadratic formula. So what I will always do is I will always multiply everything by -1 if that first term is negative like that. It doesn't change the solutions at all, but it does make the beginning term positive. It changes all the signs, but it's easier if that first term is positive. Don't forget the quadratic formula. And as college algebra students, you never know when the quadratic formula is going to come up, so that's just a formula you need to know. So here I have x equals the opposite of b. In this problem, a is 9, b is -1, and c is -3. So you have the opposite of b, which would be 1 plus or minus the square root of -1 squared minus 4 times 9 times -3 divided by 2 times 9. So you get no you don't. You get 1 plus or minus the square root of 1. And let's see, -4 times 9 is -36 times -3 is positive 108. That's nice. So you get positive 108 divided by 18. And so that gives me 1 plus or minus the square root of 109 over 18. And so the way the problem is worded when I'm looking at this on WebAssign, the way it's worded, it says enter your answers as a comma-separated list. And you have, in WebAssign, it looks like this, x equals, and then you have the answer box sitting right here, like this. So what you're going to have to do there is just enter a list of zeros. The first zero is negative, is 3. We knew that one. And then comma separated means you put a comma then, and then you can't do plus or minus. You have to enter each one of these separately. So you have 1 plus the square root of 109 over 18, and then comma 1 minus the square root of 109 over 18. Like that. And that's the way you'd have to enter it on WebAssign. So, and you'd have to be careful how you enter it to make sure that you enter it, or that the arithmetic you enter is correct. So you have to use the little palettes that come up to enter that correctly, probably. So, Amber, is that
okay?
It's certainly not a trivial question. So,
no, I guess I didn't know how to get that unfactorable.
Right. So the quadratic formula, when you have a quadratic like that, and if it's not factorable, then your only choice is to use the quadratic formula.
Okay, yeah, that's where I had saw that actually looking for a different solution on another problem, so I will go back and try and use that on the ones that I couldn't factor down.
Okay.
So
all right.
That answers my question.
Do you have anything else?
Not right now.
Okay. Then what we're going to do today, so we're going to go on and talk about inverse functions. And that will allow us to be in a position where we can start talking about exponential and logarithm functions next week after the exam. So our next lecture will be next Wednesday. So that will be November the 1st, believe it or not. And so then we'll be ready to start talking about exponential and logarithm functions. So today's deal is we're all about talking about functions that are inverses of each other. What that means, actually kind of look at a definition and how to look at and work with inverse functions, how to find functions that are inverses. All right, something that we're going to need to be able to do the rest of the semester with exponential and logarithm functions. So if we start off with these two functions, f of x equals x cubed minus 1, and g of x equals the cube root of x plus 1, like that. And we compose these two functions. Now remember what composition is from last time. There's two ways to compose functions. One is f circle g of x, and the other one is g circle f of x. There are two different orders. The definitions are that f circle g is defined to be f of g. It means we're going to stick the g function into the f function. And then the g circle f is defined to be g of f. It means we're going to stick the f function into the g function. All right, and so when you do that, on the first one, when you have f of g, this would be f of the cube root of x plus 1. And that would say go to the function f. Every place you see an x, I'm going to drop in the cube root of x plus 1. And so when you do that, you get the cube root of x plus 1 cubed, which is just x plus 1 minus 1, and that gives you x. And so what we have here, in the, first of all, is we have that, I'm going to write this down at the bottom, that f circle g of x, or f of g of x, for this particular set of functions is equal to x. I made these functions up, by the way, so this was going to turn out. I knew that this is the way it was going to turn out when I made these two functions up. But notice what it kind of means at the end is that when you operate with g and then f on x, it's kind of like you don't do anything at all. When you've got f of g of x, it's kind of like f and g cancel each other out, and you're just left with what you started with, which is x. If you compose the functions the other direction, you go g of f, so that would be g of x cubed minus 1. And then we go to the function g, we write that down. Every place we see an x, we substitute x cubed minus 1. So g was cube root of x plus 1. So this would be the cube root of the x is x cubed minus 1, and then you still have that plus 1 in there. And so that gives you the cube root of just x cubed, because the 1's add to give 0, the negative 1 and the positive 1. And that also gives you x. And so notice when you operate the other direction, when you do g composed with f of x, or g of f, once again, g and f kind of cancel each other out when you operate with them like that, where you first operate with one and then you operate with the other one. These properties, these two statements right here, are sometimes called inverse cancellation. And this means that f and g are inverses of each other. This means f and g are inverses of each other. This is sometimes used as the definition for inverse functions, as two functions are inverses if when you compose them in either direction, you get x as the answer. And that property is sometimes referred to as inverse cancellation. Calculus students use inverse calculation kind of to their advantage frequently. All right, if you draw the pictures that we talked about last week for composition, so for example, if we look at f of g of x equals x, and we draw these little pictures out with domains and ranges, you know, we start with x, and for g, f of g of x, g is the function that starts first on x and takes x to g of x, but then notice what f does. F then takes g of x and it takes it back to f. like that. And if you look at those two arrows show very clearly that G and F kind of do the opposite. G takes one value to another. F goes the other direction and takes them the opposite direction. So, for example, in our problem right here, if I pick an x value, like I pick x equals, I don't know, 4. If I pick x equals 4, notice that f of 4, remember f is x cubed minus 1, so f of 4 is 4 cubed minus 1, or 64 minus 1. So f of 4 is equal to 63. Now look what g does with 63. G of 63, go to the function g, that's the cube root of 63 plus 1, or the cube root of 64, which is 4. So notice that g of 63 is equal to 4. And if you look at the very bottom there, look what you get. You have f of 4 is 63, and g of 63 is 4. F and g do the opposite, not the opposite, they do the inverse there, in that f takes 4 to 63, g takes 63 to 4. Anytime two functions have this property, this inverse cancellation property that I'm highlighting here kind of in a red, anytime they have this inverse cancellation property, they're inverses, and they're going to do exactly what we saw at the very bottom there. They're going to switch their x and y values. All right, so that's a key to two functions being inverses of each other, is that they have this inverse cancellation property, and that inverse cancellation property means that they actually switch x and y values. All right, and these two functions, now I picked 4 and got 63. I could have used any x value I wanted to in these two functions, and they would always switch the x and y values, no matter what x and y values you got here. They would always interchange them. All right. Now, if we continue to look at those two functions that are inverses of each other, you have f of x is x cubed minus 1, and g of x was the cube root of x plus 1. Those are the two I was looking at. If you look at their graphs, so we're kind of going through and looking at different features of functions that are inverses of each other. If you look at their graphs, x cubed minus 1 is the cube function shifted down 1 unit. So if I'm going to graph x cubed minus 1, it's our cube function, which we know from earlier in the semester, shifted down 1 unit. And so this is our, and you could plot points to get the same graph if you wanted to. But this is the graph of x cubed minus 1. This is the graph of f right here. Now notice what g, its inverse, what its graph looks like on the same coordinate system. If you took the, one way you could graph this, by the way, is you could take the 3 points that I've got on x cubed minus 1. That would be 1, 0, 0, negative 1, and negative 1, negative 2. Remember, what inverses do is they interchange, or they switch around x and y values. So I could do that with those 3 points, and I would get 0, 1. All I'm doing is switching the x and y values. I get negative 1, 0, and then I'd get negative 2, negative 1. Notice I just switched around the x and y values, and that graph, it's the cube root graph, and that graph actually looks like this. And that's the graph of G. And what I want you to notice is that there is actually some symmetry going on there, that if you draw in this diagonal line at y equals x, this 45-degree line like this, this is the equation y equals x, that these graphs have symmetry around that line y equals x. And we can actually write that as kind of a property that inverses always have graphs that are symmetric around the line y equals x. That's always true. All right, so we're, by the way, we're going to summarize all this stuff as we write it down. We've got a couple of things going on here so far. We've got three things, actually, we've talked about for inverse functions. We've got inverse cancellation that I have right there. We have that inverses switch or interchange use the word interchange there also, interchange x and y values. And I'm going to go ahead and highlight that one also. So we've got those two properties right there, inverse cancellation and the fact that inverses switch x and y values. And now we've got this next property right here that inverses always have graphs that are symmetric around the line y equals x. When you switch x and y values, you get symmetry around that line. So that what that means is if I give you a graph, you could graph the inverse of that function pretty easily. So given a graph, sketch its inverse. Okay, so let's say I have a graph, and I'm just going to make something up here. Let's say I have a graph that starts over here at -4, -2, comes up here to -3, 0, and then goes way over here to 1, 2, 3, 4, 5, 5, 2. And it's just a couple of line segments like this. And this is the graph of our function f. Then f inverse, that graph, we could sketch that easy enough by just interchanging the x and y values for each of the points on this graph and using the fact that the two graphs have symmetry around y equals x. So this point right here was at -4, -2. This one was at -3, 0, and then 5, 2. So we take those 3 points and we interchange them, and we get -2, -4 right here. And then we get 0, -3 right here. And then we get 2, 5, which is way up here. And so we get this graph. Let me do that a little bit better. This graph like this. And that would be the graph of f inverse. And I'm going to use that note. I haven't used that notation yet, so well, let me go ahead and use it now. So there, that notation right there, the f with a little -1 that looks like an exponent, that's the notation for f inverse. That's red f inverse. And notice you do get that symmetry around the line y equals x. You can always sketch in that line y equals x. And you see that you've got symmetry about that line right there. All right, now this does, unfortunately, when you're talking about graphs, it does bring up a complication for inverses that we do need to talk about, a little bit at least. And that is if you take a graph like, for example, the square function, and try to look at its inverse. So let's just look at the graph of f of x equals x squared. So f of x equals x squared, we know, is a parabola that goes through 0, 0, and 1, 1, and -1, 1. It also goes through -2, 4, and +2, 4, like that, and you get this parabola like this. Well, that's fine. If you try to look at the inverse for this function, in other words, you interchange the x and y values, well, you get 0, 0 and 1, 1, but you get 4, 2. You also get 4, negative 2, and you also get 1, negative 1. And you get this graph like this for the inverse. Now, the problem here with that graph, besides the fact that I didn't sketch it all that great, but the problem with that graph is that the inverse, in this case, is not a function, right? It fails the vertical line test. And the reason why that graph failed the vertical line test is that the original graph, and remember, by the way, when failing the vertical line test means that you get repeated x values. You have repeated x's, right? So when I draw a vertical line here on our inverse, you've got 2 points that have the same x value, right? This one is at 4, negative 2. This point's at 4, 2. They have the same x value. You can't have repeated x's and have a function like that. Well, where did those repeated x's come from? Well, the repeated x's came from the fact that the original graph had repeated y's. The original graph, it was a function, but the original graph had repeated y values. And notice what that meant was when it had repeated y values, that I could draw a horizontal line that intersected that graph in two places. So this graph fails what we call the horizontal line test. And graphs that fail the horizontal line test have inverses that are not functions. Let me write that down. Graphs that are let me repeat that. Graphs that have repeated y's, in other words, they fail the horizontal line test, have inverses that are not functions. Because they fail the vertical line test when you look at those. And we don't want, if we're talking about inverses, we don't want graphs that have inverses that are not functions. So we don't want this kind of situation. We don't want graphs that have repeated y's or that fail the horizontal line test. We only want to look at graphs that pass the horizontal line test. Like our function a few minutes ago, the x cubed function at the top of the page, the one in f, that one definitely passes the horizontal line test. And so its inverse is definitely a function. So in both of those graphs, in fact, in both cases in this page, pass the horizontal line test, right? Our original functions in both cases, original functions in both cases passed the horizontal line test. In other words, they did not have any repeated y values. So their inverses were functions. They also passed the vertical line test. So functions that pass the horizontal line test, the functions that pass the horizontal line test, in other words, no repeated y's, functions that pass the horizontal line test, no repeated y values, are called, first of all, one-to-one functions. And their inverses are functions. These are the kinds of functions we want to talk about, functions that pass the horizontal line test, and these are called one-to-one functions. All right, that's actually a property for inverses right here. We want to highlight this right here, that these are the only kinds of functions we want to talk about when we're dealing with inverses, are what functions that are one-to-one or that pass the horizontal line test. So I would want you to be able to look at a graph and tell me whether it's one-to-one, whether it passes the horizontal line test, and then go from there as far as talking about its inverse. Now, on the square function, sometimes what you can do, so sometimes you can take a function that fails the horizontal line test, in other words, not one-to-one, and restrict the domain so what you have left is one-to-one. In other words, passes the horizontal line test. And then has an inverse that's a function. Now I know that sounds complicated, but look at the square function. Okay, so the square function we know fails the horizontal line test. It's not one-to-one. So we're going to draw it in again. And we write underneath it, fails the horizontal line test, not one-to-one. Inverse is not a function. Right? And so what we do is we take this graph and we restrict the domain. We restrict the domain. And what we do is we restrict it to x greater than or equal to 0. And when we restrict the domain to just x values greater than or equal to 0, the new graph, when you've done that, is just the right side of the parabola. You're only using x values greater than or equal to 0, and so you just get this piece of the parabola. You don't get the other half. And notice when you do that, so this is x squared with x greater than or equal to 0. This is just x squared. And what happens in this case? Now the inverse, if you look at the inverse of this graph, the inverse looks like this. It's just the upper half of this parabola that opens to the side. And that function is, or that graph is a function. So what did we do? We took the original graph, we restricted the domain, we just looked at x values greater than or equal to 0, and we got a graph that passes the horizontal line test. So this one is one-to-one, and the inverse is a function. That's the kind of problem we want to look at. We just want to look at one-to-one functions, functions that pass, when we're talking about inverses, we want to look at functions that pass the horizontal line test. Sometimes you have a function, if it's an important function, like the square function especially, where you can restrict it so that what you have, a function that's not one-to-one, you can restrict it so that what you have left is one-to-one. the we only do this typically with functions that are kind of important. And in mathematics, like for those of you who are going to go on and take more math classes, like if you're going to go on and take trigonometry, and you look at the sine graph, one of the single most important functions just in general in applications, incredibly important function. The problem with the sine graph is that it fails the horizontal line test. Not only does it fail it, it fails it miserably. You have a graph that looks like this, and this is sometimes called a sine wave, and this graph just keeps on going like this forever, right? Never stops, and so it fails the horizontal line test. And so what trig students have to do is they have to restrict the domain. I'm not going to get into it all what the restriction is in general here. That's for trig students to worry about. So don't worry about that here. All I care about is that you worry about the fact that you're restricting the domain on this graph so that what you have left is 1 to 1. And so they restrict it to just this piece right here. And that piece passes the horizontal line test. This one passes. Let me write that better. Passes the horizontal line test. And so this graph is 1 to 1. And its inverse is a function. The first graph failed the horizontal line test. It was not 1 to 1. Inverse is not a function. So I do want you to kind of understand this restriction process a little bit. And then I want you to understand what a one-to-one function is. That a one-to-one function is one that passes the horizontal line test. Those are important ideas, I think. All right. So the next thing I want to talk about is finally is how do you find the inverse of a function given the equation. So given the equation of a one-to-one function, how do you find its inverse? And that's actually a two-step process, and you're just using the basic ideas behind inverses. What you're doing is you interchange x and y, you switch x and y, and then you put the equation in function form, you solve for y. This is kind of the last big thing to talk about with inverses. And then we're going to kind of piece all this together and look at a decent number of problems. Interchange x and y, solve for y. That's the two-step process for actually creating an inverse function if you're given an equation. Not a graph, but an equation. All right, so let's look at some examples of that. So f of x is equal to 3x minus 5. That's our function. And what I want to do is I want to find the inverse of f. Find the inverse of f. So in symbols, this is the way it would be read or written. Find f inverse, where you have f with what looks like a -1 as an exponent. This is not an exponent. It's just notation. And you just read that f inverse. So don't read as f to the -1. Definitely not. Do read as f inverse. Right, that's what that notation means. All right, now f of x equals 3x minus 5 is a linear function. Its graph is a line. Graph is a slant line, in fact. Right, it has a slope of 3 because that's in slope-intercept form. And so this is definitely a one-to-one function, right? If you think about it, the graph of a line, all lines except for horizontal lines, all lines pass the horizontal line test. So the graph is a slant line. It definitely passes the horizontal line test. And so this function is one-to-one. So it's okay to look at its inverse. So what do? We write, instead of f of x, we write y equals 3x minus 5. And then, like I just wrote on the last screen, we interchange x and y. So that means wherever you see a y, you put an x, and wherever you see an x, you put a y. Because that's what inverses do, is they interchange x and y values. So you're just taking advantage of that. All right? And then you take that's the inverse, actually. It's just not in a very nice function form. And so then you solve for y. In other words, you get the y value by itself. So I add 5 to both sides of the equation. I divide by 3. And that's my inverse function right there. Now, usually you write it with inverse notation. So you write, instead of y, you write f inverse x. Right? F inverse of x equals, and then this is x plus 5 over 3, and that's our inverse function. So these two functions that I'm boxing off right here are inverses of each other. Now you could get an idea whether you're right or not. Now this is just an idea of whether you're right or not, but do they switch x and y's? Do they interchange x and y's? So pick an x value, anything you want, like let's say f of 6. F of 6 is 3 times 6 minus 5, or 18 minus 5, or 13. So f of 6 is equal to 13. Then look at f inverse of 13. F inverse of 13 is 13 plus 5 over 3, or 18 over 3, or 6. And so sure enough, f inverse of 13 is equal to 6. Now this absolutely positively does not prove that they're inverses of each other. All this proved is that they interchange 6 and 13. So to prove, but this does give you a good idea that you're probably right, that they interchange the x and y values for these two. We just kind of picked 6 out of thin air. And so we have a pretty good feeling here that we're right here, but we don't know for sure that we're right. But we can prove that these are inverses of each other. So same functions here. So you have f of x is equal to 3x minus 5. F inverse of x is equal to x plus 5, x plus 5 over 3. Like that. So to prove these are inverses, you have to show that they always interchange x and y values. And to show that, what you're doing is looking at the composition. You're looking at inverse cancellation. And do these functions have this property that when you compose them in either order, like this, that they cancel each other out, that you have this inverse cancellation property? So to prove that two functions are inverses, you actually have to go through this composition and show that you get x as the answer for both compositions. So in our problem, we have two functions, f and f inverse. Now we just hope it's f inverse here. But if you look at f composed with f inverse of x, that's f of f inverse of x. F inverse of x is x plus 5 over 3. So we just plug in what what that's equal to. Right, that inside function here. There's my f inverse x. I replaced it with x plus 5 over 3. And now this says go to the function f, and every place I see an x, I'm going to put my little parentheses there, and I drop in x plus 5 over 3. And notice what happens. The 3's cancel, and boom, you've got x plus 5 minus 5, you get x. Yay. So what did we just show here? We just showed that f composed with f inverse of x is equal to x. Now what do you have to do? Technically, you have to show this composition works in both directions. It is possible to make up cases where when you compose them in one direction, you get x, in the other direction, you do not get x. Mostly has to do with functions that have restrictions on them where that would happen. I'm not going to make too big a deal about that at all. So we're looking at f inverse of f of x. So this is f inverse of f, which is 3x minus 5. So here's f right here. Here's f, 3x minus 5. And now I go to the function f inverse, which is x plus 5 over 3. And instead of an x, I drop in 3x minus 5. And so you get 3x minus 5 plus 5, which is just 3x over 3, or x, yay. And so I get f inverse composed with f of x is equal to x also. Amber, I know you're there. I'm just going to pause for just a second. I need to go take care of something real quick. So I'm just pausing the video, the recording, and I need to step out. Okay, I'm not really sure what that was. Something crashed in the other room, but I can never find anything, so I guess everything's okay. All right, so to prove two functions are inverses of each other, we just show both compositions are equal to x, and then we've got it. So we've actually got most of what we need to get done here. I do want to look at maybe a little bit more complicated problems for finding the inverse. So let's say this is problem, well, this is going to be a problem that I'm going to make up. Let's say we have f of x is equal to 1 over 1 plus x, and we want to find f inverse. All right, so what do? We in place of f, we first just put a y in its place, and then we go through this two-step process. So we switch x and y. So we interchange x and y here. So we have x equals 1 over 1 plus y. And then we solve this equation for y. And that's a little bit tricky on this problem, to solve for y. So to solve for y, we get rid of the fractions, first of all. And to get rid of the fractions in this equation, what we've got to do is multiply both sides of the equation by 1 plus y. So getting rid of the fractions, I multiply both sides by 1 plus y. And so that gives me x times 1 plus y equals 1. And then I multiply this out using the distributive property. You get x plus xy equals 1. And then I subtract x. And then finally divide by x. And there's my inverse. And so you have f inverse x is equal to 1 minus x over x, like that. Now, are these inverses? Can we get a good idea that these are inverses? So let's, here's my function f up here. Here's what I think my function f inverse is down here. And I'm a little bit concerned because this was a little bit harder to solve for y in this problem as to whether I'm correct or not. So what we could do is we could pick an x value. This doesn't prove anything, but it gives me a good idea that I might be right. So for example, I could pick x equals, let's say, -2. So if I pick x equals -2 and I look at f of -2, I get 1 over 1 plus -2. So f of -2 is 1 over -1. F of -2 is -1. So then what do I hope here? I hope that f inverse of -1 is equal to -2. So I look at f inverse of -1, and that gives me 1 minus -1 over -1. And sure enough, it works, doesn't it? Because I get f inverse of -1 is equal to 2 over -1. So I get f inverse of -1 is equal to -2. Does not prove that these are inverses, but it does give me a pretty good idea that these are inverses because they did interchange those x and y values. Definitely doesn't prove anything. I'd have to go through the composition to show that they, or to actually prove that they're inverses, which I'm not really going to do in this problem at all. I'm not going to hold you responsible for finding compositions of too complicated of a situation like that. So, all right, so we're closing in on being done with functions that are inverses. So a couple of things here that I want to kind of go back over and review before we finish this up. So first of all, and one other thing I forgot to mention in these two functions right here. So if I have f of x is 1 over 1 plus x, and we got that f inverse was 1 minus x over x, like so. These are functions that are rational functions. This is something we've just come out of talking about in class a week or so ago. These are rational functions. And because they're rational functions, so a lot of times they have vertical and horizontal asymptotes. Well, remember the vertical asymptote is where the denominator is 0. And so on the original function, on 1 over 1 plus x, the denominator is 0 and x is -1. And so you get x equals -1 as a vertical asymptote. And then the horizontal asymptote, well, the degree of the numerator is less than the degree of the denominator. And we talked in class about the fact that when the degree of the numerator is less than the degree of the denominator, that you always get a horizontal asymptote at y equals 0, or the x-axis. Now look at the inverse function. Look at the vertical and horizontal asymptotes for that function. The vertical asymptote is where the denominator is 0, but the denominator is 0 when x is 0. And the horizontal asymptote, well, the degree of the numerator and the denominator are the same in this problem. And so if you recall, what I talked about doing is saying, look at the dominant terms in the numerator and the denominator. So you get negative x over x. The dominant terms, remember, are the terms with the biggest powers. And so that's just negative x over x, which is -1. And so the horizontal asymptote's at y equals -1. And what I want you to notice is that the vertical and horizontal asymptotes for these two functions actually switched around. They interchanged. And that should happen anytime you have vertical and horizontal asymptotes and you have inverse functions, is that they should always interchange x and y values. That will absolutely always happen. All right, so to kind of finish this up, I actually think that we're probably finished up with this. Now, there's not much else to do. So functions that are inverses. Let's just summarize everything that we've talked about. So f and g are inverses. We're going to kind of write everything down here at one time. So what does that mean? First of all, that f composed with g of x equals f of g equals x. And g composed with f of x is g of f. That's equal to x. Remember that this property is called inverse cancellation. Next thing, if f and g are inverses, f and g interchange x and y values. In other words, if f of a is equal to b, then g of b is equal to a. Remember that notation-wise, that f inverse is read, or when I write f to that -1 right there, remember that's read f inverse. And that's our notation for an inverse function. All right, remember that the graphs of inverses are symmetric around the line y equals x. Right? Remember that only one-to-one functions, and remember one-to-one functions are functions that pass the horizontal line test, have inverses that are functions. Right? Functions that are not one-to-one, that fail the horizontal line test, their inverses are not functions. Right? So not one-to-one, in other words, fail the horizontal line test. Inverses are not functions. All right, and so that I could, I'm going to go ahead and actually cut all this off of this page right here and paste it onto the next page. I'm going to cut that, paste it onto the next page so that I can get everything for inverses on one page here. And so finally, the last thing here, to find f inverse given the equation for f, we have a two-step process. Interchange x and y. Solve for y. Right, so we've got definitely some properties. We have the inverse cancellation property. Inverses interchange x and y values. We have this notation for inverses. You read that f inverse. Graphs of inverses are symmetric around y equals x. Important. And when we're talking about inverses, we're only talking about one-to-one functions, functions that pass the horizontal line test. Finally, if you interchange x and y and solve for y, you can actually create an inverse given the equation for a function. And we've seen a couple of examples of doing that. All right, so that kind of summarizes everything for inverses. The homework from the textbook. Is on page 264 of your book. And I want you to look at problems 7, 9, and 11 on that page, and problems 23 and 24, 25 and 27, and 33 and 35. Okay, so this finishes up our discussion on inverses. We're going to be ready to talk about exponential and logarithm functions, which are inverses of each other, next time. Any questions before I shut down the lecture for the day? Amber?
No questions here yet.
Okay, so I have office hours tonight. I have office hours on campus on Tuesday and Wednesday of this week. Everyone have a great week. Please let me know how I can help you prepare for this exam too. I'll be happy to help you out. People are emailing me questions, and those people who are emailing me through WebAssign or whatever, I'm answering those and trying to respond. So please either email me, come by my office, online office, come by my face-to-face office this week, get some help. You have a good review for this test, so work on that review, and I will hopefully see you soon. Good luck on exam 2.